So, taking a look at some more on velocity and acceleration in space. 3 dimensions, more or less. I mean, some 2 dimensions, I guess, but all right. So yeah, say we've got a curve, and the particle is following along that curve. At a particular time t, we can set up hopefully a vector type function. That'll give us that position, if you will, at a time t. And to go all the way through it here, going back to our old days a little bit, if we then come out a little bit more time, say an h time, amount of time of h, and so we've got a different position for our particle. Well, that vector is then r of t plus h, right? So what would we get if we did, again, just kind of review some things. What if I set up a formula, equation? What would that information provide us right there? The vector at t plus h minus the vector at t divided by h. Okay, which is the also known as the what? Yeah, it's this. Yes, okay. It's the average velocity, right? With what we're talking about right now. That's the average velocity, which is, yeah, the secant line between P and Q here. The slope of that secant line. But now dealing in vectors, it's a vector. But yeah, that would describe that velocity between those two. That would give us a velocity vector. So it gives us a velocity at between those two times. And then if we take the limit as h approaches 0 of that average velocity vector, what is that going to give us? Well, that gives us the instantaneous velocity vector. Okay, just kind of reviewing. They went through some review stuff in the book, so I thought I would also too with you. All right. And of course, what would the speed of our vector at time t be? Yeah, it's the magnitude part. Be the magnitude of our velocity vector, right? That would be the speed of our particle on there. Yeah, just the magnitude of the velocity vector. And of course, we also know this this right here to be what is that in terms of the r vector? What is this velocity vector? What is just this right here? This is the derivative. Yeah, is the derivative. So yeah, this is also, so this equals the derivative, which I think we've mentioned that already, but kind of going through it a little more here. In terms of velocity. Okay. All right, well, of course, tied into this then, if we take the derivative of the velocity vector, which would be the second derivative of the position vector, we've got our acceleration, right? Vector of acceleration. So the acceleration vector is the derivative of the velocity vector. Second derivative of the position vector. Okay. All right. So anyway, it all goes back to the same old thing we've always been dealing with in calculus. All right, so yeah, start off kind of easy here. Find the velocity, acceleration, and the speed of the particle with position vector r fingers aren't doing too good racing here today. Position vector r of t equals t plus 1 I plus t squared minus 1j plus 3k. All right, so yeah, it's pretty straightforward. The velocity vector is just the derivative position vector, so that would be what? 1i plus 2tj plus 0k. So it's just I plus 2tj. The acceleration vector then is just the derivative of the velocity, right? And so that would just be 0i plus 2j, so it's just 2j. Pretty simple acceleration. And then our speed, well, that's the magnitude of the velocity vector, right? So that would be the square root of 1 squared plus 2t squared. So that's square root of 1 plus 4t squared. So we could find the speed at any particular time t we wanted based on that formula right there. All right. Now, what they'll also have us do is this. Okay, so same. Oops, probably should have noted those. All right, so b of t, what was it? I plus 2tj. Acceleration was just 2j. Okay, yeah, those weren't hard. All right. Okay, so here's what else I'll do. So let's sketch the path of the particle. And then draw the velocity and acceleration vectors at t equals 1. Okay, so we've got to sketch the path of the particle here based on our position vector right there. What do you see? Well, the z component is constant, right? It's always 3. So in our x, y, z coordinate system, yeah, we've always got a z value of 3. So that tells us basically the height of it if x and y All right, so basically we got to figure out what happens in the x and the y, and we just think of those as the parameters, parametric equations. X equals t plus 1, y equals t squared minus 1. And to see what maybe that looks like, just convert it to an xy equation is usually what they try to get us to do. So if we change this, yeah, solve one of them for t, which makes sense here to solve this one for t. T on this one would be, what, x minus 1? And then we can just plug in that for t. So we have y equals x minus 1 squared minus 1, which is a what? What is it? Y equals x. Yeah. That'd just be a parabola, yeah. So in the xy plane here, we've got a parabola. Let's see, that would be vertex at 1, negative 1. We're just talking about in the xy plane. So we've got this parabola in the xy plane with vertex at 1, negative 1 going upward, yeah. All right, and so if we put that in the three-dimensional world here, that's what we've got in the xy plane, but the z component adds it, says it's at level of the 3, right? Our z is, yeah, so here, if we look at our vertex, 1, negative 1, so it's here and then back, so then we go up 3 to the z, value 3 there. So yeah, we've got our parabola here that's that parabola, but at level 3 in the XYZ plane. Now, we want to put then also these velocity vector and acceleration vectors on there at t equals 1. So at t equals 1, what have we got for a velocity vector? Well, that would be I plus 2j. So we've got it a 1, 2 vector. Basically 1 in the x, 2 in the y. There's no k component, so it's staying at the same level. So at t equals 1, where are we on the on our graph at t equals 1? Well, that would be, position would be 2i plus 0j plus 3k. So it's 2, 0, and 3. Yeah, just on the other side of the vertex here. 2, 0, 3, so put it right there. So that's our position. And so, or that's our terminal point of this position vector. And so now we put in this vector on that, 1, 2, which just means basically go out in the x direction 1 and in the y direction 2. So that would put us where? So we need to go 1 and then 2. So that would put us like that. So we translate that. I think they want it usually on the curve, so it'd be parallel to that or whatever. Okay? And then the acceleration vector is just at 1 is 2j. And so that's 0 to 0, right? Everything's 0 except the y component. So 0, 2, so that would just be right along the y-axis. Straightforward. That's our acceleration there. All right. Okay. Any other questions on that? Oh, good? Okay. All right. Okay, so this one, next one here, find the velocity and position vectors of a particle with acceleration vector 4ti plus 6tj plus k and initial position r0 equals just I. Initial velocity v0 equals I minus j plus k. All right, so we kind of have to go the other direction on this one because we were given the acceleration, and so since we know that the acceleration is the derivative of the velocity vector, what is the velocity in terms of acceleration? That would be the integral, right? And so we're just going to integrate our acceleration vector to find the velocity vector. Well, that would be, integrate that, just do it component by component. What, 2t squared for the I, plus 3t squared for the j, and then t would be the k component. And of course this is an indefinite, so we need a constant. And this, the only thing is it's a constant vector. Since we're dealing in vectors, it'll be our constant vector. That's our velocity. Now, it just so happens that we can figure out the constant vector because we know the initial velocity vector is I minus j plus k. So if we plug in, if we just plug in 0 for time t, which that's what we're talking about for initial velocity, time 0, t0. Okay, that makes that 0. So basically, plugging in 0 to this gives us the constant vector. There's nothing else added to it. And we know from our given that v0 should equal I minus j plus k. And so that basically tells us our constant vector is I minus j plus k. So that means the velocity vector turns into 2t squared I plus 3t, all that, plus then that. So what's the velocity vector if we combine the I components and the j and k components? So we have 2t squared plus 1i plus 3t squared minus 1j plus t plus 1k. There you go. So that's our velocity vector right there in this case. All right. Now what else do we want? Position vector. All right, so we've got our v of t. Now we want our r of t. And how are we going to get that? Yep. All right, we know that v of t is the derivative of the position vector. And so the position vector is going to be the derivative, the integral of the velocity vector. Yeah, so we're going to integrate this. It's the integral of 2t squared plus 1 I plus 3t squared minus 1 j plus t plus 1k So what does that give us? 2/3 t cubed plus t I plus t cubed minus t j 1/2 t squared plus tk plus a constant vector, which we called the first one c, so we'll call this one d. All right, but again, we once again notice that we can complete this, get the d vector by the given information is the initial position, the vector at 0 is just I, and we note that if we plug in 0 to what we've got, that's 0, that's 0, that's 0, so d is the R0 which is I. And so if we plug that in there, all that adds then is something to the I. So R of t, position vector, would be 2/3 t cubed plus t plus 1, right? Because that's 1I, so we just add the 1 there. All right, plus t cubed minus t j plus 1/2 t squared plus t k. All right. Is that okay? So far, so good.